So you can slice a cone in a way that you just get a point. You can slice a cone in a way that you just get a line or intersecting lines. You can slice a cone in that you can get a parabola. So we had a section about parabolas. But you can also slice a cone in that you get a circle or ellipse. Remember, a circle is just a special type of ellipse. Ellipse is more general, circle is more specific. But that's where we were on Friday before break, I think. Section 10.3, ellipses. And so we had our standard equation for an ellipse. Pieces of an ellipse. We have a center, we have foci, we have vertices. Now vertices are technically, you could call them major vertices and minor vertices, but the main vertices are just on the major axis. So they're technically, I think when our book talks about vertices, it's just talking about the endpoints at either edge of the major axis. That's how we find them. And how do we know the difference between major or minor? What do those names even denote, guys? Who is the major? Who is the minor? Yeah, and you can tell which one's longer. Good, good, good. It's just like whichever one's longer. I'm taking attendance real quick. Melanie, okay. Hopefully she's not one of the poor ones that got sick. I heard a lot of them got sick. And then Thomas is in choir too. And then otherwise, we're all here. Okay. Jacob's in choir too? I forgot Jacob was in choir. Have any of you guys been following their pictures or snaps or whatnot? I've seen a couple from Nicole Goldman, but I was seeing if you guys have seen anything from the choir kids on their trip. We just heard this morning they weren't feeling so good. All right, kiddos, if you don't mind, let's go ahead and pause the recording a little bit on hyperbolas because they're hard and it might be nice to split them up as much as is possible. We saw Friday, the major, the minor. We saw that it looks like a circle. Did we actually get back and fill in that little bit of notes that I had skipped? Yeah. A circle, we have the standard form, divide by r. It looks a lot like an ellipse. The only difference is a circle, the A and the B is going to be the same. They're both going to be just R. So they're going to be the exact same, whereas with an ellipse, it's going to be a little bit different because it's stretched differently horizontally than vertically. We already talked about major is just the longer one. Minor is the smaller one. And remember, when you square root these, you only get half the distance. You only get the radius. We made a couple mistakes on that, I think, on Friday. Sorry, Thursday. Friday was Good Friday, huh? On Thursday. Then we talked about the foci for ellipses, how to solve for them. And the foci are C units away from, or a distance of C away from the center. So we're going to have to either add C to the H or add and subtract C to the K, depending on the orientation of our ellipse. So we had gotten this example totally done. Did you guys finish it in your notes, or did I just finish it? I think we finished it. We got that one? Oh, because we had started this one. Okay. So we got one example totally done. We had another example or two or three. Okay, we have a couple more still to try. So let's see how we're doing, and we can review at the same time and try to get back in the swing of things, huh? So this is where we ended on Thursday. Find the standard form of the equation of the ellipse, having foci at 0, 1, and 4, 1, having a major axis length of 6. Oh, this was an important clue that confused a few of you. So when it's a major axis length of 6, is that the whole thing or is that half of the thing? The whole thing. So the entire axis was 6, which is why we had to cut that in half and square that for our A. And we knew that it was supposed to go here, not here, because of how our foci are horizontally apart. But also they gave us a picture that helped a little bit. And then how did we get this guy? That was from the halfway between the foci. Yeah, we had to use the formula for C, right? So C squared equals A squared minus B squared, a little different than what we're used to with Pythagorean, but we're not doing right triangles anymore. And then we solved by plugging in our C equals 2 and squaring it, plugging in our A equals 3 and squaring it, and then just solving. So We didn't get to talk about eccentricity, but I think I had you guys quickly write down the formula. Did I? So you could use it? Okay, but not all of you might have. So let's make sure we get down eccentricity. Eccentricity is kind of like the, I even put it in quotes up there, the ovalness, how elliptical the ellipse actually is. You can think of it as being a measurement that kind of shows how squished it is or how non-circular or circular it is. Because something can be an ellipse and look an awful lot like a circle. And the nice thing is with eccentricity, you don't really have to solve for anything new. It's more like just taking two quantities that you should be able to find anyway and just making a ratio out of it. I want to give you a little bit of a better understanding of what the ratio means, but let me let you guys finish writing it down so you can focus a little bit better when I do explain it. And so you might not have remembered what we did. Well, I guess I did it. You guys were watching. But on Thursday, how I had the two magnets, and I had the string, and I showed that as I traced the string with my marker, the string with some set distance between those two foci. As I traced the string, I made an ellipse. And if the foci were really close together, it was going to be more like a circle. And if the foci are literally on top of each other, if C is 0, then it would be a circle because it'd be one set radius, like a compass that would go all the way around. But as the foci become more and more and more apart, the distance between them becomes greater and greater, then the more elliptical the ellipse will be. And that's kind of what's being shown up here. If C is really small, the closer C gets to 0, the closer E gets to 0. So the smaller E is, the more circular the shape. And the larger E is, the more elliptical the shape. But the crazy thing is that, well, as you look at the picture question, will C ever be greater than A? Why not? A is actually, yeah, comprising the shape, and C is some distance inside. Does that make sense? So by definition, C has to be less than A, so the eccentricity is only going to go between 0 and 1. This ratio can never go beyond 1 because C can never go beyond A. C has to be within, and A is the outer boundary. So E is naturally just a really small number, a really small ratio. But if you think about fractions, okay, so if E was, for instance, 5/8 or 7/8 or 9/16 or 15/16, all of those would be fairly elliptical. And the closer E gets to 1, the more elliptical I have, because that means C is getting closer to A. But the farther C is away from A, hence the closer E is to 0. Whether 1/10, 1/100th, 1/1000th, if C is really, really tiny, then that just means it's going to be more circular. And why does it make sense that if C equals 0, that it is a circle? Can anybody actually explain that to me? If C is 0, it is a circle, not an ellipse.
Then it just becomes one dot instead of two.
Yeah. It just becomes one dot instead of 2. And if you think about it mathematically, couldn't we also say C squared is equal to A squared minus B squared? If C is 0, what's going on? And if A equals B, wouldn't that go right back to, oh, hey, we're just dealing with one set radius r? Does that kind of make sense? You wouldn't have two different measurements. You just have one, and that one would go all the way around the shape. So anyway, that's just a quick little explanation as to how to keep track of what the eccentricity is talking about and what's going on, like if the eccentricity is really small or really big. Woo-hoo-hoo! This is a party. Someone tell me what we're supposed to be trying to do. Okay. How do we get there? Mathematically, how are we going to try to accomplish the task being given to us of, yes, you're right, find the center, vertices, foci, and the eccentricity, and sketch. How do we get there? Put it in standard form. So we have to remember, what does standard form look like? This? Well, this is standard conic form. Yeah. Bless you. Welcome. I'm going to write it like this. The problem is I'm not exactly sure who's A or who's B until I start doing some dividing. Some of you might be like, well, the Y one is smaller, so he must be B, and the X one is bigger, so he must be A. Well, maybe. But here's the long story short. To get from here to here, don't we have some work to do? Someone tell me something. How can we get one step closer? Sure. We can subtract 37. What's something I might do over here? Group. $54, thank you. Why am I leaving kind of awkward spaces? I do want to complete the square, but before I can complete the square, I do need to, I heard it, factor. So, do I need to factor out of everybody? No. They're two separate expressions, right? Okay, so just factor out of each one individually. Oh, I was using that, wasn't I? Thank you, thank you, thank you. I didn't realize why I wrote plus 4, but it was because I was looking there. So minus 54x. What happens when you factor out the 9? Now careful, I'm not pulling out the x. Some of you are like, factor out the x. No, 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 no. I need to have a perfect square trinomial, right? So don't factor out the x, just factor out the 9, because I need to get a leading coefficient of 1. Which is why I'm just going to factor out the 4 and not the y. Did you guys double check my other expression? I wrote that right? 4y squared plus 40y. Good. So what's missing? I'm not going to call it C, but I will say I'm missing my perfect square. How could I make it a perfect square? Divide by 2, negative 3 and negative 3 squared? 9. So why am I writing a 9 there and an 81 here? Not because of 9 squared, not technically, because if this was an 8, it wouldn't be. Does that make sense, John? So it's 9 times whatever's on the outside, which will be 81. So I took that negative 6, I cut it in half, and then I squared it. I'm just completing the square. So you guys finish it off and simplify. Let's see where we're at. Let me give you an extra 60 seconds. Fill in the other blanks using a similar process. Simplify. You have some numbers to put together and combine. I think that's where you should get, but do you know why? I think that's where you should get, but do you know why? How'd you fill in the blank, Andrew?
Or which one? Pretend y is 25.
25. Why was it 25?
Because 10 divided by 2 squared
10 divided by 2 is 5. 5 squared is 25. And you also said 100. That's weird. Why'd you say that one? Good. Look on who's on the outside. Need to keep everything balanced. Did you guys double check my math? Is it 144, 181 minus 37? What else did I do over here? Yeah, simplified. Technically, I factored. Technically, I showed my perfect squares, right? Once we complete the square, the whole point is that we can go ahead and make them into their little squared factors. But how do I keep going in order to get another step closer to what I need it to look like? It's not supposed to be equal to 144. Ooh, subtract 143. Awful idea. Divide by 144. Now, subtracting would get you 1, right? But I want to divide because I need division in order to be able to see my standard form. So divide everybody by 144. Ha-ha, there's my 1. Ha-ha, there's my fraction. Well, careful. Some of you are like, oh, it's a circle, but it's not a circle. Why is it not a circle? Did you forget about your poor little 4 and 9? Is there a way to reduce 9 and 144 and 4 and 144? Ooh. So dividing 144 by 9, you do end up with 16, because it's 1 and then 54. Yeah. Does 4 go into 144? And even if it didn't, I could multiply top and bottom by 1/9. Even if it wasn't pretty, I would still have some expression that's different than 144. Even if it wasn't pretty and nice. And same thing over here. I could multiply top and bottom by 1/4. Even if it wasn't pretty and nice, I would still have a different quantity. But you guys divided and you ended up figuring out that 4 goes into 144 36 times. Hey, hey. That looks pretty good, yeah? So identify some stuff. What do we got? Who's the center? 3, -5. Who's my, even though we don't necessarily need to write it because of what they asked, who's your major radius? Careful. Major? 6. So technically, is my formula technically completely right? Who ended up being the larger, being the major? So technically. But we didn't know for sure until we did it, so it doesn't really matter. Tons and tons. We just know the larger one is the major one. So the major radius, remember, square root it, is 6. What's the minor radius? Yeah. Look at the other term, square root it. They didn't ask for it, but we're going to put it in our picture anyway. What's our focus? How do I find that? Technically, foci, there are 2 of them. Good. C squared is equal to the larger minus the smaller, right? So 36 minus 16, a squared minus b squared. Yeah, so c is going to be the square root of 20, which, hey, doesn't 4 go into 20 5 times? Square root of 4 is 2, so 2 root 5. We're going to get back to our foci in just 1 second because I really think visualizing is going to help so you don't just have to memorize how I get the foci, because I'm visualizing it when I'm thinking it through. But we can do the eccentricity really fast, right? Because isn't eccentricity just taking c, right? And dividing by who? A. Good, which would be 6, which we could reduce to be root 5 all over 3. So far we have our center, we have our major, we have our minor. Let's start doing our picture and then see if the foci just kind of naturally flow out. Ooh, I did not draw that correctly. Oh. 1, 2, 3, 1, 2, 3, 4, 5. Major radius. Why am I going to erase this picture one more time? To make my units a whole lot smaller. I need to go 6 in what direction? Up and down, because where's my 36? Underneath the y's. Does that make sense? So since 36 is the measurement or the coefficient, 136 is the coefficient of the y, then I need to go ahead and go vertically, 1, 2, 3, 4, 5, and 6. There's my vertex if they needed me to say it. Ooh, it does say vertices. Okay, so there's 1. That's going to be at 3, 1. Here's my center at 3, negative 5. And where's my other vertex going to be? Good. Because for my vertices, I just need to add 6 and subtract 6 to my y value, right? Uh-huh. So Colby's thinking, wait a minute, so if you're on the major axis, isn't that where the foci go also? And so the foci say 2 root 5. Colby is trying to think 2 point something, but careful, that 2 point something is the root 5, right? We still have to do that 2 point something times 2. So it'd be 4 point something. The 2 point something will be pretty small because it's 5. You have to get to 9. It would be less than 5, I think. Could be around 5. But either way, we could go 1, 2, 3, 4-ish, somewhere between 4-ish and 5-ish, put a foci. 1, 2, 3, 4-ish, somewhere between 4 and 5-ish, put a foci. But here's the long story short. The foci, couldn't I write it nice and neat by just saying 3 and negative 5 plus or minus 2 root 5? Does that make sense, guys? Well, the struggle is that the foci are actual points. So if you do the y equals, you're telling me lines. So does that make sense? Like you're naming it wrong, kind of. But it's a good thing to think about. Like, oh, if the major is vertical, then I'm going to go ahead and add to the y value. If the major was instead of vertical, horizontal, what would you be adding and subtracting from? The x value instead. I almost have my shape. What am I missing? My minor radius is 4, right? So I have 1, 2, 3, and 4. And then I have 1, 2, 3, and 4. Roughly. Dun, 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 dun. Dun, dun. So the only thing we didn't get to actually write down, I looked back in the directions after I'd stopped writing. We didn't write down the vertices, but we technically already found those too, and I think the picture hopefully helped with those also. In that they're going to be vertically away from the center, so 3. You could just do negative 5 plus or minus 6, but we figured out that's the same thing as 3 and 1, and 3 and negative 11. Someone look over this entire problem. Actually, all of you, and let's just see what you come up with. My question to you is the following. How could this have gotten messier or nastier or disgusting or thrown you for a loop? Okay, if it's cubed, it wouldn't be an ellipse. So then no, that would throw things horribly off. But you won't see that in this section because it wouldn't be a conic. So good, but you're not going to see it here. Okay, what else could go wrong? No, like what else would, if it hadn't worked out as nicely, would have made it harder on you? If it was a nasty complete the square, so maybe, hi microphone, maybe if it hadn't been pretty numbers, like if you had had something like 5 here, right, 5 halves and 25 fourths, it might have been nasty as far as the numbers. Someone also said something with 16. What were you talking about? I liked it though. Yeah, what if when you, well, maybe if it was not a perfect square, right? So you wouldn't have had like 4 and 6, so that would have been nasty. Or what if this had been nasty, right? What if that hadn't even been a nice number? So there's a lot of nasty numbers could happen. Nasty numbers could happen in completing the square. Nasty numbers could happen here when you're simplifying. Nasty numbers could happen here when you're square rooting. Okay, so nasty numbers. Can I show you one more thing though? What if you had done this and it would have equaled 0? If it was 0, you can't divide by 0, because Ryan's like, wait, you divide by that number and you can't divide by 0, so impossible? What if it was 0? Do you know what would happen if you had gotten it to be 0 instead? You would have gotten all of this work. You would have been able to get this side, but it would have been equal to 0 instead. Can we just peek at that real quick? Just quick pretend. What if, help me out real fast, was it x minus 3? And y? Plus 5, except we also had a 9 and a 4. Okay, what if we had gotten equal to 0? Yeah. Push this homework through tomorrow. What would this thing have been? It's not an ellipse. It's a degenerate. Wait, it's a degenerate. Remember degenerates? It could be a point, it could be a line, it could be intersecting lines, or it could just be impossible. How could we have figured it out? What if we had... what if we had subtracted somebody? They both have squares. Let's just square root them both. But wait, what do you see when I try to square root? It's imaginary. So is this a real shape? Well, kind of like that. So you have to say imaginary, right? Now the crazy thing is when we get to hyperbolas in the next section, 10.4, we're going to have a minus instead of a plus. And so if that one ever became 0, actually there would be none of this imaginary stuff. And if you would have plus or minus square rooted both sides, you could have square rooted and you would have really just had 2 plus or minus lines. Degenerate. Interesting. The degenerates come out of you trying to do the process of getting to an ellipse or getting to a parabola or getting to a hyperbola, and something goes wrong. One example would be this equaling 0. Another example of something going wrong is what if this was a negative? If it was a negative, it would also be a degenerate, and it would also be, in this example, if you were to subtract. Ooh. I think that one would also be imaginary. I was trying to do it quick in my head. So I want you guys to be aware, just in case something funny comes up in homework. We don't have tons of time. So if you want, I can go ahead and throw the homework up on the screen. I'm hoping a lot of you guys already started it, because it'll make your tonight better. But if you didn't start it, oh well, hopefully your spring break was better, and tonight will just be a homework you have to do for tomorrow, yeah? Homework sheets, chapter 10. Quick heads up, there are only 2 more sections that we're doing in chapter 10. I think 2. One from our book, which is 10.4, and one from a different book. It's going to be a handout, which has something to do with taking a conic and spinning it. Ooh. That'll be exciting. Not that kind. If you guys want the homework, you can take a picture of it. Sorry, sometimes the different versions got weird. Right here, 10.3. And then 10.4, and then the handout, and then we're done. Don't worry, we'll take a couple days on each of the other. But check out your calendars so that you don't get behind. You guys good? Ellipses tonight? P.S. You might want to start studying formulas. Think about it. It makes sense. You might want to start highlighting, formula carding, etc. Bye, cool kids. Happy Monday. Yeah.